Thank you. And above all, thank you for inviting me here. So I'm going to bring the subject of quantum mechanics a bit closer to classical physics. And as a start, I also want to name some collaborators there. So I'm going to tell you something about turbulence in quantum fluids. So what is turbulence? Well, I guess everybody has some kind of intuition for turbulence. Typically, when we travel, we are on a bumpy flight, and I really do not really spend time telling you that turbulence is inside us. For example, the air flows in the in the trachea, in the bloodstream, in the aorta, which is turbulent flow, and there are many things which we build which depend on turbulence, like airfoils, jet engines, etc. Around us, we have the air, the atmosphere, the climate, the oceans, the interior of the Earth, which is turbulent, solar plasmas, etc. So turbulence is everywhere, and that should be enough of a motivation. From the physics point of view, if we go beyond the actually practical applications, engineering applications, turbulence is a fantastic problem of nonlinear statistical physics. I want to show you this image of a pyroclastic flow from a volcano, because when you look at that and you sort of figure out the typical length scales involved, you notice that there are essentially eddies. There is motion taking place over a huge range of length scales, from the kilometer size of the image to the millimeter. So we have decades, really, of length scales which are excited simultaneously. They interact non-linearly. So it's quite a problem of nonlinear statistical physics. And also mathematically, it is intriguing that there is actually a Millennium Prize problem left to solve to win $1 million, which is actually worth much less than when the prize was set up. But it is actually it's considered by fluid dynamicists an important problem, the possibility of finite time singularities of the Navier-Stokes equation, which actually would have an impact on our understanding of turbulence. Now, since we are in Rome and there is so much artwork around here, I want to tell you a bit about the classical turbulence before we go to quantum turbulence, using an image from a painter, however, who lived in Milan, not in Rome, I want to stress. So it is a waterfall, a small waterfall coming into a pond. And this is a striking drawing because usually artists represent turbulence as some kind of unstructured foamy mass. But here, Leonardo da Vinci actually noticed, he was a keen observer of nature, he noticed that the turbulence consists of eddies. So I've added some colors. In blue, you see essentially the direction of the velocity field. And in red, the direction of the local rotation. In modern notation, clearly Leonardo did not know any modern notation. He never went to school, so he never took a course of vector calculus. We call the curl of the velocity field the vorticity. So that is the local rotation, and the red lines indicate this local rotation. So when you look at this picture, you need to imagine that there are vortex lines, there are infinite vortex lines everywhere. Now, this representation of turbulence is deep, as I said, because it is at the basis of our current understanding of turbulent flows. And here we need to say that the simplest of all turbulence problems which we want to study is homogeneous isotropic turbulence, which is far away from boundaries, which is maintained in a statistical steady state by continually forcing the turbulence at some large length scales, typically some agitation using propellers, for example, or solar input in the atmosphere. So what we have in this turbulence, which is isotropic, which is homogeneous, as I said, we have actually a cascade of energy from the large length scales of the injection. So there are eddies which are unstable, break up into smaller and smaller eddies, as you see in this figure on the left, schematically. And in this process, actually, viscosity is not relevant. The viscosity of the fluid, which would eventually kill off the turbulence, matters only at the very small length scales, that is, the large wave numbers. I use the wave numbers as a measure of the inverse length scale, where actually the kinetic energy of the rotational motion is turned into heat. So this idea is due to Louis Richardson, so it dates back to the early 1920s, and it was refined mathematically by Kolmogorov in the 1940s, who found, and that is possibly the most relevant, important result of turbulence theory, he found that the distribution of the kinetic energy over the size of the eddies, that is to say the wave numbers, scales like k to the minus 5/3, which is the famous Kolmogorov spectrum. And you see at the right-hand side what it means. So most of the energy is at the left-hand side, large length scales, small wave numbers, and there is an energy flux towards the high wave numbers, which is called the energy cascade. Now here comes now quantum mechanics. So you all know, of course, that Bose and Einstein predicted that bosons can, if cooled sufficiently, they actually pile up in the ground state and create microscopic quantum effects. So the quantum fluids, which I'm going to consider here, which are relevant, there is some information about turbulence, are essentially superfluid helium, both isotopes, helium-4, helium-3, cold atoms, also polariton condensates, and in astrophysics, there are some systems which are quantum fluids. So quantum turbulence is what I refer to as the turbulence of the quantum fluid. Now, there are two properties which are really striking in quantum fluids. One is superfluidity, that is to say, in comparison with classical ordinary fluids like air and water, the absence of viscosity. Now, this property follows from the dispersion relation. But above all, it's the quantization of the circulation which is the most striking difference. So we have a macroscopic complex wave function with an amplitude and a phase, and we know that the velocity which we associate to that is proportional to the gradient of the phase. So the implication for the turbulence is quite important, because that means that if we measure the circulation, which is the line integral of the velocity around the closed curve, a typical measure of the intensity of a vortex, if you measure it, we obtain either 0 or a fixed number, or a multiple integer of that. This fixed number is called the quantum of circulation, and it is Planck's constant divided by the mass of the relevant boson. Now, you need, however, that for this number to be non-zero, that the path of integration encloses a hole. That is to say, your domain is multiply connected. You may say, how do I create that? Of course, externally, we can put a wire across our system, and we can create a hole. The wire excludes the fluid. But such holes can form spontaneously, a process called vortex nucleation, and so we obtain vortex lines or quantum vortices in general. So what is a quantum vortex? Imagine some kind of mini tornado. So a typical tornado represented on the right has a core size which is, 20, 50 meters, 100 meters. Imagine we have actually a very elementary tornado. The core size in helium-4, for example, is about angstrom size, so it's very, very thin. And around this mini tornado, the circulation is fixed. In other words, the strength of the vortex is fixed by Planck's constant. And the fluid which is rotating about the axis of the mini tornado actually has 0 viscosity. So it keeps rotating. The rotation keeps going without being dissipated. Now, in the figures, you see in the middle a picture of the phase, because it's actually the phase which changes between 0 and 2 pi as we move around the axis of the vortex, which is actually what causes the velocity field to drop like 1 over the distance from the axis, like in a well-known textbook of elementary fluid dynamics. And that is possible because the density, the magnitude of the wave function, drops to 0 on the axis. So in other words, the axis is a singularity of the phase, because it will be the ratio, the phase will be the arctangent of the ratio of the imaginary part divided by the real part, which both. So we have a phase defect, or a tornado, but of fixed strength. Now, which kind of configuration can we create with quantum vortices like that? Well, the most known configuration is the vortex lattice. So you take your system and you rotate it, and then the vortex lines would form spontaneously coming from the boundaries, and you get a nice vortex lattice like shown at the left-hand side. But it's possible to create a disordered system of vortices actually in many, many ways. If, for example, we can agitate the system, we can shake it, we can input some heat energy, we can stir it with some propellers in case of liquid helium, or a laser spoon in case of atomic condensate. And we create many vortex lines which will form a very disorganized configurations as schematically represented on the right-hand side, where you see schematically, you see two blue propellers counter-rotating, therefore driving the flow in some kind of flow pattern called the Von-Karman flow, which in England people like to call the French washing machine. Now, what is actually a better representation than the schematic representation I've seen? Well, this is actually some numerical work. We see in a cubic domain, we see a tangle of quantum vortices. So this is a snapshot. So this should give you an idea of what is quantum turbulence, at least in liquid helium. So we have all these vortex lines which interact. So there are lots of physics taking place. The vortices move each other, so interact via the velocity field which they generate. They also collide. There are vortex reconnections. We keep changing the topology. There are undulations along the shape of the vortex lines, which are called Kelvin waves. Lord Kelvin derived the dispersion formula for such waves in 1880. So this picture is often referred to as the tangle of the vortex tangle, which is synonymous of quantum turbulence. So which kind of properties such a system has? So these lines are essentially delta functions, vorticity lines, and we see the vorticity here directly, like in the red sketches, which I added to Leonardo's drawing. You don't see the velocity field, which is utterly complicated in such a system, of course. And you must also imagine that the fluid, which is actually moving around the lines, which you see, is, if the temperature is low enough, is essentially a pure superfluid. So it is essentially a rotational solution of the Laplace equation without viscosity. In other words, the immediate suggestion which would come to the mind is that, well, isn't that something which is some kind of simplified turbulence, perhaps some kind of skeleton of turbulence, which we achieve with a quantum system rather than with an ordinary fluid? Now, there have been many experiments of such a system, and here I want to show you one, for example, some experimental results obtained in Grenoble on the left-hand side. So here they measured actually the velocity fluctuations, and this graph shows a very clear indication of the Kolmogorov spectrum measured in this kind of superflow wind tunnel, which you see schematically represented. So now this Kolmogorov spectrum falls into a range of wave numbers between the inverse of the system size, essentially, the diameter of the channel, and the inverse of the distance between the vortices. Because if you look at this picture again, it's clear that here we have actually automatically some other characteristic length scale, which is the average distance between the vortices. So we must distinguish between what happens over scales which are larger than such distance and scales which are smaller than this distance. And the reason is that numerical work and also theory has shown that all these vortex lines, which are all tangled up, like actually to form bundles. The numerical picture at the right-hand side shows the bundle essentially indicated by some kind of light yellow. So regions where the vortices are parallel to each other rather than somewhat random to each other. And those are the red lines. So these vortex bundles, or if you want, partially polarized bundles, because they are in the midst of complicated, random vortex lines, is what causes the Kolmogorov spectrum. So the bundles essentially mean that the velocity field is coherent, and therefore there is large energy within the bundle. And that is essentially the reason of the formation of the Kolmogorov spectrum. And this is remarkable because also the numerics of the Navier-Stokes equation show that classical turbulence is not some kind of uniform mass, but there is a spontaneous formation of regions of high coherence, of high vorticity, aligned vorticity, similar somewhat to such bundles. However, this is not the end of the story, because if it were so, I would say, oh, well, it looks like quantum turbulence is a bit of reproducing classical turbulence with many quanta, with many vortex lines. It is not the case at all. Some other experiments revealed other regimes, other types of quantum turbulence. For example, there is a type called Wiener turbulence to contrast it against the previous type of turbulence, which is somewhat with classical property, with the Kolmogorov spectrum, which we refer to as the Kolmogorov type. So these two pictures try to illustrate the difference. On the left-hand side, the kind of Kolmogorov type of quantum turbulence, similar to classical turbulence. So you see visibly here, we see some kind of bundling, some bundles. There is a Kolmogorov spectrum that is the signature of the energy cascade, which is responsible for the world where we live. And this turbulence is also noticeable in the experiments, not only because of the spectrum, which can be measured, but also by the way it decays. It decays with that power law, T to the minus 3/2. At the right-hand side, this numerical picture shows a typical Wiener kind of turbulence. This is more like a random flow. So there is no Kolmogorov spectrum. The energy does not pile up at the smallest achievable wave numbers. There is no energy cascade, or the cascade is very, very weak. It decays in a different way. The correlation function is quite short. So it's really, I would say, if I had to summarize its property, it's more like a random flow. Do we know actually why we have two types? Not really well. I mean, it seems that it depends on the kind of injection which we can actually produce, and we can actually, in the same experiment, produce both types of turbulence. Now, a good example of this second non-classical turbulence, to me, is the thermal quench of a Bose gas. So what is the exercise? Well, the exercise, which can be done experimentally and numerically, is to take a system of bosons, a gas of bosons, and imagine that we start with some uniform occupation number, which is essentially uniform up to some cutoff, for example. But the phase is random. So and then we let the interactions to proceed, and what you will see, and that is the picture at the top right-hand side, you see the momentum spectrum. You see at the bottom, you see like a red step, which is the initial condition. So uniform occupation number up to some cutoff in wave numbers, and you see actually what's going on. There is a pile up of particles into the low wave numbers, essentially creating a condensate, and also energy flows to higher wave numbers. And eventually, the two processes saturate together, and eventually the system thermalizes. So you see that in this case, in this process, we go through a transient regime of turbulence represented in the picture below, very intense turbulence which decays. So you see actually how this kind of turbulence, Wiener turbulence in particular, is essentially a transient state between an initial condition which is very much out of equilibrium, and then the final condition is in equilibrium. But there is not only this cascade, there is not only this Wiener turbulence, which is definitely not classical, there is also another process which is similar to the cascade of eddies conjectured by Richardson and then discussed mathematically by Kolmogorov, essentially responsible for the Kolmogorov spectrum, but it is actually a cascade of waves on individual vortex lines. So even if the lines are actually somewhat random towards each other, you see in the schematic diagram, you see a kind of a Kelvin wave on a long vortex, and you see that actually if you have a Kelvin waves of finite amplitude which nonlinear interact, what they do, and that was an idea of Swistunov, a brilliant idea in 1995, he found that actually waves interact and generate shorter waves. So we can have a cascade of waves, of Kelvin waves, rather than eddies. In other words, we can actually have a system with a double cascade towards high wave numbers. And this can actually take the energy to such large wave numbers that energy can be lost by radiation, sound radiation. That is to say, phonons. And that is really the ultimate heat sink at very low temperature. And there is, this year, there's been an experiment done in Helsinki, which for the first time, actually, after many years, gave some experimental evidence of this idea. At the right-hand side, you see a calculation in which you see the two cascades, the cascade of eddies a la Kolmogorov and the cascade of waves a la Kelvin, waves on the vortices, with the kind of bottleneck region, the flat region in between. But also turbulence can be created in condensates, and there are groups who are doing experiments of this kind, particularly in Brazil, in Bagnato's group, and in Cambridge, and they managed to create a turbulence in condensate by shaking or oscillating the system. And there is very good evidence which this experiment produced of a cascade. And the numerical simulations of the experiment suggest something like represented in the picture. So some cloud of atoms, which is shaken very much. So the density oscillations are very large. And they are similar to a turbulent system of waves, a classical system of waves, which was studied years ago by Zakharov, who predicted the spectrum. And the theory of Zakharov is based essentially on kinetics, the interaction of various waves in the weakly nonlinear regime. So it's a weak turbulence theory. But here we have actually a strong regime, because together with these very large waves, we have also vortices, represented here as red and blue loops inside the system, which is shaken and clearly turbulent. And I want to say that actually the problem of turbulence is actually expanding because there are other systems where we think there is turbulence. And here I have two examples. One is neutron stars. Neutron stars are superfluids in the interior, a superfluid of neutrons. And we know that essentially they lose energy by radiating waves. So the crust spins down, but there are sudden, apparently random glitches, which you see represented in the diagram. So the changes of the angular velocity, and of course we cannot go there and actually measure, and we cannot do anything in the lab, which is really similar to the extreme physics of neutron stars. But the basic idea is that there is some kind of avalanche of vortices which are pinned in the crust or pinned to the essentially proton flux tubes in the interior, and they suddenly move, a bunch of vortices move, creating an avalanche, and then changing the angular momentum, which we can observe. And also more recently, turbulence has come up also in the subject of dark matter. So there are models of dark matter that we're not very sure, of course, of that. So if dark matter is some kind of light bosons, it can be described as some kind of condensate, and which is self-gravitating. And the picture on the right-hand side shows in yellow the very intense region, which is essentially corresponding to a galactic halo. And those pink lines are essentially vortex lines around the galactic halo. And these lines actually have been noticed. They are vortices, and even the turbulence of these vortices, it's a clear Wiener kind of turbulence. And finally, I want to say that because of the discrete nature of the vorticity, we can actually know exactly where the lines are, so we can tell whether they are knotted or not. So we can actually study the topology of a turbulent fluid, which is very difficult to do in air or water in a classical system. And the recent work has shown that indeed the quasi-classical regime of turbulence is actually knotted, and the picture actually is a calculation of vortex lines represented with different colors, and the knot which is visible there is some kind of very extreme high-order knot that can be measured by knot polynomials, for example, the Alexander or Jones or Confly TP polynomial, and the distribution of the knots obeys a scaling law. So there is a knot spectrum. And more intriguing, some numerical work has shown evidence that when this turbulence decays, it decays along some kind of topological cascade or some kind of preferred route, and we don't really know why. So somehow the topology puts some restrictions on the dynamics. And many properties which are visible in this vortex system or magnetic flux systems when they're knotted are similar to what long molecules, for example, DNA, do. So it is quite an area of activity. I think I'm running out of time, and I want to simply draw some quick conclusion. So there are various types of quantum turbulence. There is a classical-like turbulence where it seems that on sufficiently large length scales, quantum turbulence is similar to classical turbulence. In other words, if you put together many quanta of circulation, you obtain semi-classical results. But there are many other features like binary turbulence, the Kelvin wave cascade, the strong turbulence in condensates, which are not necessarily classical. They are new physics, and we know very little about. There is another aspect which I want to stress, that when there is a similarity between quantum turbulence and classical turbulence, well, actually, it's interesting to see this property from the point of view of building it using many quanta. And so that's a kind of geometrical way of recreating, of understanding classical effects. So there is a kind of physics which is learned coming from the discrete nature of vorticity and building up essentially a continuous limit. For example, the universal properties of vortex reconnections, which are fundamental in both classical and quantum turbulence, have been discovered in the context of quantum turbulence. And finally, I want to stress how multidisciplinary this problem is, because it started essentially in the context of condensed matter physics, low temperature physics, helium. Then it moved to atomic condensates, and then there are also polaritons, essentially semiconductors, and there are these applications of astrophysics. So it's really a problem of many scientific communities coming together. And at this point, I stop and thank you.